Welcome. I'm Ayan Chakrabarti, the General Chair. Hello, everyone. Welcome to ICCP 2020. This year, the conference is being hosted by Washington University in St. Louis. Now, of course, we had hoped to see you all in person in St. Louis and welcome you to our beautiful campus. But because of the COVID-19 situation, we have had to sort of adjust our plans and switch to the virtual format. Nevertheless, we have a great program planned for you that we hope you'll find to be just as informative and stimulating as an in-person meeting. We have 3 keynotes from distinguished speakers, 32 technical paper talks divided across 8 sessions, 42 spotlight videos of posters and demos. Our conference homepage is going to be your main stop for participating in the conference program. All our keynote and paper sessions will be streamed live, which you can access by clicking on this button. Please also take a look at our program page to see the schedule of these sessions. Please note that all times are in Central Daylight Time, which is the St. Louis time zone, so be sure to adjust for that. We have a clock on that page to show you the current local time in CDT to help you calibrate. Now, when you tune into a live session, you'll be able to ask questions by using the live chat window on the right of the video. If you're seeing this live, you can probably see the live chat window right now to your right. Please send in your questions as the talk is happening, as well as during the breaks for Q&A, in between papers, and at the end for keynote sessions. Session chairs will sort of then curate these questions and then read them out to the speakers and authors. Now, in addition to live sessions and interactions through live chat, a lot of the interaction in the conference is going to happen asynchronously as well. All poster and demo spotlight videos are already up on the conference website. You can interact with authors of these spotlights and posters and demos in the comment section of these videos. Also, videos of the live paper and keynote sessions will be available through this part of the conference homepage. And these videos will be available after the stream ends. So you can catch up on these videos if you missed a session, but more importantly, for paper sessions, we expect that the discussions and Q&A will continue asynchronously after the session ends in the comment threads of these videos. So it's not just the 3-minute Q&A during the live session, but we expect that you will keep on interacting, the attendees will keep on interacting with the authors through these comment sections throughout the conference. So we have defined periods of time for these asynchronous discussions listed on the conference schedule, but in general, you can sort of do this, you can post comments and respond to them anytime, and these will essentially be open throughout the duration of the conference. Now, on the conference website, you can also click on that button to download proceedings. The papers that are appearing in the PAMI special issue are going to be available for free download throughout the duration of the conference. To download the proceedings themselves, you will need a password, which we have emailed to all folks who have registered, and that password should have been included in your welcome email. In addition to sort of the technical parts of the conference, there's also sort of the social component. So every year, ICCP has had this tradition of all attendees gathering together to take a group photo. Now, clearly, we can't do that this year, but we decided we still want to have a group photo to sort of commemorate the fact that we were all virtually together at ICCP. And so what we're asking you to do is to take a selfie of yourself attending the conference, learning about computational photography while still being responsible and socially distant and so on, and click on that button and upload that selfie. And at the end of the conference, we'll stitch all of these together to form a group photo. We also have a Slack team for general social interactions. You can go and sort of like catch up, see who else is attending, catch up with them through direct messages. We also have in that Slack team virtual booths, which are public channels for our sponsors, which is something that you can sort of use for networking and so on. Again, an invitation to the Slack channel should have been, you should have received that invitation as part of your welcome email. So let's now go on and talk a bit about the program. So we have 3 distinguished speakers giving keynote talks. There's Ira Kemelmacher-Schleicherman, Aude Oliva, and Mark Itzler. Then we also have the technical program, which is our 32 papers divided across 8 sessions. This year, we sort of had a novel publication model. We have a joint collaboration with the the Transactions on Pattern Analysis and Machine Intelligence, PAMI, for a special issue on computational photography, which is actually going to be published fairly soon in the coming months. And so what we did is that the papers submitted to ICCP were reviewed simultaneously for acceptance to be presented in the conference and published either in the conference proceedings or directly in the special issue. And all of the papers that were accepted are being presented as talks at ICCP. You can find sort of a more detailed description of this review process in the beginning of the conference proceedings. So just some statistics. This year we had 74 papers, complete paper submissions, which is an ICCP record. This is an increase from 47 submissions in 2019. Of these 74, 32 papers were accepted, which is sort of a 43% acceptance rate. And 9 of these 32 were actually selected to be published in the PAMI special issue. So that corresponds to sort of a 12% acceptance rate for the special issue papers. The other part of our program are the posters and demos, and this is again has been a tradition at ICCP. These are not considered archival. These aren't considered to be published at ICCP. And so what this means is that we ask folks to sort of submit work that is, late breaking results that is yet to be published or has already been published elsewhere in sort of like a related community. And this helps them come and tell us about that work and sort of, gives them visibility inside sort of the computational photography, the more focused computational photography community. So next, I want to sort of thank all the organizers who have sort of helped us make this happen. David Forsyth, Kalyan Sunkavali, and I acted as program chairs. Katie Bowman and Yanis Kikulekas were our finance chairs. Jin Wegu and Achuta Kadambi were our industry chairs handling sponsorship. Sarah Abramson, Matt O'Toole, Sanjeev Kopal handled posters and demos. Suren Jayasurya is our social media chair and will be sending you Twitter blasts and sort of figuring out ways for us to be social on Slack. Ashok Veeraraghavan and Vivek Bhuminathan were our publication chairs. Abby Stalianu is our local arrangements chair, and Chihao Sia is our website chair. We also had 56 expert reviewers on our program committee who helped us review all the papers, make these decisions, and so on. I also want to specifically thank our PAMI editorial advisors, Kristen Dana, Ko Nishino, and Sven Dickinson, who helped us, who facilitated this entire new collaboration, which we tried for the first time, and sort of helped us make sure that the whole PAMI process went smoothly, gave us feedback, gave us recommendations, and did that. They put in a huge amount of effort, to sort of turn this around quickly, and as we navigated this new publication model. I also want to really thank our sponsors, Adobe and Kaust, who were our platinum sponsors, Google, SenseTime, Snap, ByteDance, and Akasha, who were our silver sponsors, Samsung and Omron, who are our bronze sponsors, and NVIDIA, who is sponsoring our Best Paper Award. And they sort of remained with us through our transition from an in-person meeting to a virtual conference. And we really appreciate their commitment to supporting our community. I also sort of want to thank our general sponsors. So Washington University, which really helped me organize a bunch of these things. I especially want to thank Tammy Haney, Kelly Ekman, and Sharon Matlock, who really helped out with a lot of these things. Also thanks to IEEE, which is sort of our general sponsor, and especially Momo Vana, who really helped us with a lot of the finance stuff. Okay, so taking a break from tradition now, what we're going to do is actually announce the Best Paper Award at the beginning of the conference. And we all our accepted papers were really great, but we sort of went ahead and went through this process where the program chair selected a short list of papers to be considered for the Best Paper Award. Then we sort of forwarded these to a distinguished panel who sort of evaluated them. And so this panel included Todd Zickler, Kiros Kutulakos, and Yoav Schechner. And they reviewed these papers and sort of with sort of Kalyan Sunkavali, one of our program chairs, taking notes, made the final decisions. So first I want to sort of mention, the honorable mention. So this is This is a paper titled High Resolution Diffuse Optical Tomography Using Short-Range Indirect Subsurface Imaging. This has a bunch of authors from CMU and Rice, Chao Liu, Akash Mehti, Artur Dubrovsky, Ashutosh Saudral, and Srinivas Narasimhan, who's from CMU. And this paper is going to be presented in the afternoon session on Sunday, 3B. So that's the honorable mention. And finally, it's time for the best paper award itself. And that goes to the paper titled 1-Bit Time Resolved Imaging by Ayush Bhandari, Miguel Heredia Conde, and Otmar Lofeld. And so this is a really innovative paper, which we all, I think, enjoyed reading. And this is going to be presented in the session on Saturday morning, session 2A. And so let's congratulate the authors. And there's going to be their award. The award this year is a NVIDIA GPU, which is being sort of sponsored by NVIDIA. So it might take some time for you guys to actually receive that award because till sort of like folks get back to slightly normal operations. So you might have to be socially distanced from your GPU for a bit, but we'll make sure that you get it. And congratulations again. All right, so that's the welcome to ICCP. We hope that you have a really interesting, informative, stimulating conference. And without further ado, let's now move on to the first set of paper presentations.
Hi, everyone. Welcome. I'm so sorry I can't see you all in person today, but I know by looking at the set of papers that we have on the schedule that we really have an excellent ICCP this year. So I'm so excited to help kick off the first session of ICCP. We have a great set of papers in this session, all that have a theme of recovering information in the presence of attenuation and scattering, from seeing through atmosphere and through underwater to recovering properties from scattering clouds and other kinds of materials. So today's first paper by Iris Tal and collaborators is on new insights and a new network approach for dehazing images. So Iris will be here for questions after the talk. So during the talk, please make sure to enter your questions into the comment section, and then I'll be able to choose from them and ask her some of these questions afterwards. Okay, so let's kick it off.
Hello, my name is Iris Tal and I am a master's student from Tel Aviv University. I'm going to present our work today, which is called NLDNet++, a physics-based single-image dehazing network, which was done in a collaboration with Yael Beckerman, Avi Mor, Lior Knafo, Jonathan Alon, and Shai Avidan. So I'm going to talk about first a short introduction, and then I'm going to explain a little bit about the algorithm we based our work on, which is called non-local image dehazing. Then I'm going to talk about our classical extension to non-local image dehazing, which is called NLD++. Then I'm going to describe our network, NLDNet++, and we're going to end with conclusions. So what is single image dehazing? Single image dehazing is a task in computer vision in which you wish to remove a haze appearing in an image so you can see more details that the haze originally obscures. Let's look at the physical model of haze. Imagine we have a scene with an object that has radiance J. Distant from the scene we have our observer, which is the camera. The haze particles are scattering the light emitted from the scene, so only a part of the intensity reaches the camera. In addition to light from the scene, we have the environmental light, which is called air light. The haze particles scatter the air light as well, so the same pixel of the camera receives a linear combination of light from the scene and air light. This can be described in the following formula. I, which is the hazy image, equals T, a transmission coefficient, multiplied by J, the real radiance, plus 1 minus T, multiplied by the air light. T, which is our transmission map, is dependent on the distance from the camera. So when an object is far, the transmission value is low, so we get mostly air light, and when an object is near, the value is high, and we see a truer version of the object color. The classic approach for dealing with dehazing is assuming some kind of prior on the image, and then calculating the transmission map and the air light, substituting them in our basic formula, and getting the dehazed image J. Current approaches train a network to find either the physical parameters, which are the air light and the transmission map, or the dehazed image directly. Those methods use synthetic hazy images since real data is difficult to obtain. What are we trying to solve? Our problem is it's difficult to get training data. All networks are now trained on synthesized images, and our solution is to use physics-based non-local dehazing to generate training data. Non-local image dehazing is the algorithm we're basing our work on. It relies on the small color palette assumption, which says that even though theoretically an image has millions of colors, in reality those colors form tight clusters in the RGB space, and if we replace each cluster with a cluster center, we can quantize the image to a few hundreds of colors only. Those tight clusters turn into lines in the RGB space if you look closely at the basic formula of dehazing, and those lines are termed Haze Lines in the non-local dehazing work. By calculating these lines, one can calculate also the air light and the transmission map, and then the final image is extracted. So now I move to talk about NLD++, our extension to NLD. The first thing we did is noise reduction. The problem we encountered is NLD inherently amplifies noise. Let us assume the image I is composed of the denoised image I and a general noise N. From the basic equation, we get that I equals T multiplied by J plus 1 minus T multiplied by A plus our noise N. And if we extract J, which is our dehazed image, we see that the noise is divided by T, which is a transmission coefficient. The transmission values are between 0 and 1. So we get that our noise is amplified, especially in places in the image where the transmission coefficients are low. Those are the distant parts of the scene, usually the sky. Our solution was to use a pre-processing that denoises the input before we perform NLD. Our chosen tool was VM3D. Here we can see a couple of examples where we have our input image, and we see in the original algorithm the sky were very noisy and our pre-processing corrects. Also we see here in the sky salted pepper noise that our pre-processing corrects. Our second extension to an NLD is a lower bound constraint issue. The problem we encountered, the original algorithm calculates the theoretical lower bound of the transmission map. From the general equation, if we demand that the color is greater than 0, we get that the minimal transmission value is 1 minus the minimal proportion between the hazy image I and the air light. However, the original NLD algorithm does is not enforce this lower bound on the final transmission map. Our solution is changing to an optimizer that enforces this lower bound. Our chosen optimizer is constrained linear least squares. This reduces visibility problems in dehazed image that are dark. You see here in the two examples. We have our input image. In the original algorithm, in the left, we see the image is very dark, and in our NLD++ improvement, we get back the features on the further buildings, which were too dark before. Also in this picture, in the road and in the building at the back, we get a more natural result. NLDNet++ is our network. NLD++ improves the quality of results considerably, but it comes with a high computational cost. An image that took a few seconds to process before now takes with NLD++ a few minutes. Our solution was to create a dataset of real hazy images and pseudo ground truth obtained from NLD++. We took the real hazy images from the ReSite benchmark. We specifically took the unannotated real-world images, and we trained the CNN based on this dataset. So if we have a couple of comparisons. We have a comparison on SOTS, which is a synthetic dataset, where we see we perform considerably well. We also have HazeRD, which is a dataset that is synthesized, but the simulation is more complex, and the synthesized images from this simulation are more accurate to the truth. We see our method performs very well. And OASI, the last test set we used. OASI is a dataset of real and hazy images. The hazy images are obtained from haze machines, and it's the highest quality dataset for dehazing. We see our NLDNet++ performs extremely well, revealing more details and clearing the haze where other state-of-the-art methods could not clear. We see our results. Our numeric results are very competitive with state-of-the-art methods. Another experiment we held was combining our NLD++ with Grid DehazeNet, which is a state-of-the-art method for performing dehazing published in the latest ICCV. NLDNet++ produces competitive results after being trained with 4,000 images against other networks trained with more than 100,000 images. Our idea was to take a state-of-the-art solution, fine-tune it with our dataset, and check the results. Here we have a visual comparison where we see that Grid DehazeNet fine-tune gets a very fine result. Also numerically, we get state-of-the-art and we improve from the Grid DehazeNet on the more real hazy images in almost every parameter. So our conclusions are that we create a new dataset from real hazy images. We achieve competitive results with leading methods. We managed to boost the performance of state-of-the-art method, Grid DehazeNet, on real hazy images. This technique can be applied on similar fields where real data is difficult to obtain. And we feel our research stresses the importance of using a physical model to solve real challenges in vision. Thank you so much.
Really nice results, Iris. So I have a couple of questions. As questions start coming in on the chat, I'll just ask one of my own first. So for denoising, I think you said that you used the BM3D for denoising the result, which is kind of using the same property of the original, well, different than the NLD, but it's using the same idea of like using copied similar information throughout the image to denoise. Right, so I was wondering, does using the BM3D cause any kind of biases in the recovered air light, or did you try denoising with other methods to see if different denoising techniques would have a different effect on the recovered properties?
I tried a few denoisers, and this one gave us the best results both visually and both with PSNR. So we stuck with that. We didn't see any bias in the air light.
Okay, thanks. And I guess the second question from Aditya is also about the denoising. So he says, what happens if you perform BM3D denoising after the NLD dehazing instead of before? Will you have a more noisy result or less noise result?
I will have a more noisy result because instead of canceling the noise before the process, so I will, if the dehazing is done before, the noise will be really amplified, and like to amplify it's better to first denoise the noise when it's weaker than it's amplified.
Mm-hmm. Okay, yeah, that makes sense to me. Okay, let me see. We have another one from Shayavidan. It's oh, okay, no, that's a comment. Okay, and from Suren, could the technique be applied to video when you have multiple frames, or would there be flickering artifacts? Would it be temporarily stable if you applied it to a video, basically?
So this is actually going to be our next research. So we do see in our initial results some flickering, and we need to still sort it out.
Okay. From Jenny, I have a question on the recovered result. I noticed the color is a bit different with the ground truth and also the other method. So do you have any, do you know why that might be the case?
We do see a stretching of the colors in our method, and especially in synthetic data, we see it the most, but we are very encouraged. Like when we look at, like I said in the video, when we see images that are more close to real data, this stretching actually helps remove most of the haze when other methods fail to do it. So we are aware of this issue, and maybe we need to do further research to reduce this problem.
Okay, that makes sense. So I had a question also about, so you showed this OHazy data set, which you said had a fog machine that they used to make. I'm not that familiar with it. I'm not familiar with the data set, I guess. So I'm wondering, did they have actual ground truth? Because I think for your network, you train with your NLD plus using that as the ground truth, right? So I was wondering if you compared when you used ground truth from OHazy versus or do they not have ground truth on that data set versus your pseudo ground truth?
I didn't get the question.
Okay.
Like OHazy, like it contains the ground truth because they filmed it with a haze machine, and they removed it from the scene and shot it like in a short period of time apart. So we have ground truth, but I couldn't understand the question.
Okay, this might be just me misunderstanding then. I thought that you said at some point that you were using the NLD++ as ground truth, as a pseudo ground truth to train your network. So when you train the network for OHazy, are you using the real ground truth or the pseudo ground truth?
The OHazy is only a test set. It's not in the training.
Oh, okay, I see. Okay, that makes it more clear. And okay, I think that we've gone 3 minutes. So I see that there's a lot more questions, but we can, I'll just remind everyone that there's going to be a session afterwards where Iris and her collaborators can continue to answer these questions. So thanks, Iris. It was really nice. Nice
Thank you
work.
so much.
So we're going to go on to the next paper now. So the second paper is by Amit Idis and collaborators, and it's on a ground-based approach to cloud monitoring and tomography. So kind of a complete package going from hardware to software. And I think Yoav Shetner is going to be presenting, but Amit will be here for questions after the talk. So during the talk, again, please enter your questions. If you can answer, type them in earlier, it's easier for me to then find them to ask after the presentation's over. But okay, let's get started.
We propose and demonstrate distributed imaging radiometry and tomography of the sky. The sky includes clouds and aerosols. Why should we sense them? Clouds are of course the source of rain, but they are also important for an additional reason. Globally, clouds amount to 2/3 of the Earth's albedo, modulating its energy budget. Proper sensing and modeling of clouds are necessary to reduce uncertainty in climate predictions. There are similar needs to better sense and model aerosol plumes. So what is the prevailing model? Well, most models assume an atmosphere which is made of broad uniform layers, meaning one-dimensional vertical representation and analysis. This assumption is often incorrect. The smaller clouds are, the more apparent are three-dimensional inhomogeneities and three-dimensional radiative transfer effects. These inconsistencies mislead meteorological models. The atmosphere is a three-dimensional, non-uniform, volumetric scattering medium. We seek to sense it as such. Three-dimensional reconstruction of a volumetric medium requires tomography. Specifically, it requires simultaneous multi-view radiometric imaging. Aiming at this is a space mission, Cloud CT, funded by the ERC. However, this is an exploratory project. It is not the typical remote sensing way. State-of-the-art, spaceborne instruments have superb quality and products. However, during the time it takes an individual satellite to capture multi-view images, the atmosphere changes. Spatiotemporal sampling is therefore crude. Satellites are costly and often impossible to fix. Contrary to smartphone cameras, satellites do not enjoy the economy of scale. Besides, satellites observe the clouds from the top, while many applications such as aviation need cloud-based information. Let a massive network of radiometrically calibrated cameras observe from the ground up. The network should be dense, only a couple of 100 meters between nearest neighbors. And it should be spread far out, as we explain. It observes each sky voxel from multiple directions simultaneously. The network is a unique light field imaging system that is distributed, coordinated, and scalable. In this concept, camera units are similar to smartphones. In this view, a smartphone is a camera connected via an embedded computer to the cellular network. And that's our system too. It can thus enjoy the economy of scale. The cameras are untethered and therefore placeable anywhere in the world where cellular communication reaches. They become part of the Internet of Things, reachable by all. So given coverage and internet reach, how wide can this network be? County scale, country, continental, planetary? We talk about the weather, so let us consider the UK for example. To cover the UK densely, we will need approximately 2 million sky cameras. Sounds a lot. Well, the UK already has 66 million smartphones and 6 million surveillance cameras. So our numbers are significant, but smaller than other distributed camera networks. So what are the challenges? Contrary to smartphones, all cameras should have absolute radiometric calibration and be weatherproof. Furthermore, passive sensing of scattering cannot use standard tomography. It requires new algorithms. And can such a system be shown to work? So in this work, we developed prototype technologies to make this happen. This is a prototype unit built around a machine vision camera, equipped with a fisheye lens, and an embedded computer, a cellular communication dongle, and an Arduino for controlling the mechanics. Solar power charges the batteries. The unit is untethered, so we can place it anywhere. However, in Israel we have dust and often no rain to wash it. So we equip each unit with a standard car washer to clean the lens dome. The pump is operated automatically. The distilled water dries without residue. We also created the back-end software to remotely access and control all network units, visualize their output, and perform multiple other tasks. Each camera unit underwent geometric calibration. In the field, external calibration uses observations of the sun or moon trajectories, as described in the paper Clouds in the Cloud. It is vital to perform radiometric calibration. In fisheye lens, non-uniformity calibration is challenging. We place the camera head on a gimbal and measure its response using a controlled light source. As the gimbal pans and tilts, we sample the non-uniform optical transfer across the camera's field of view. This process yields a spatial fall-off map per color channel. Using this map, we correct the raw images for non-uniformity, like this. The final critical radiometric calibration step is relating gray level values of pixels to scientifically meaningful absolute radiometric values. NASA runs HazeRD, a network of calibrated sun photometers. Here you can see a sun photometer automatically scanning and sampling the spectral radiance of the sky. During our calibration, we place each camera right near an HazeRD sun photometer on a roof. So the same angular domain is observed simultaneously, both by the camera and the sun photometer. Thanks to geometric calibration, we know which camera pixels correspond to the sun photometer samples. For these pixels, we plot the gray levels, mindful of the sun shader. Fitting the plots yields absolute calibration. For technical details on relating gray level values to the sun photometer radiance readouts and radiative transfer codes, see our paper. Later in the field, the embedded system performs high dynamic range imaging. It then runs geometric and radiometric corrections on board before transmitting back the measurements. The anchors of the network are a set of precision instruments. In addition to the sun photometer, we placed a poly-XT aerosol LiDAR by Tropos on our roof. Using high-power laser, it senses aerosols along a near vertical path up to the top of the atmosphere and as a function of time. For in situ validation, we fitted an aerosol spectrometer to a powered glider, eliminating bias by engine exhaust. This system can sample aerosol distributions above the image domain. Given a distribution of scatterers beta, the radiance field is governed by a forward model, which is three-dimensional radiative transfer, for any order of scattering. Tomographic reconstruction is an inverse problem. We solve it by fitting the forward model to data across all the data degrees of freedom. For more details on the solution principles and the implementation of efficient solvers, see our prior publications. However, prior codes for 3D tomography focused on push-boom projection to outer space. There, all voxels contribute evenly to all pixels. Our cameras are inside the medium. Modeling a single ray per pixel leads to poorly represented and recovered voxels. We overcome this by randomly perturbing the projection in every iteration of the tomographic optimization. Still, voxels that are closer to the camera affect the model and optimization gradient more strongly and more frequently during optimization relative to distant voxels. This makes the problem ill-conditioned. We solve it by scaling the gradient per voxel according to its distance. Here is the full deployment in our tests. It is in the scale of a county. This is an opportunity to thank good people, businesses, and public institutions who kindly hosted our cameras on their premises. And here are simultaneous videos captured by the camera network. We know exactly where our cameras are and their occlusions and noise specifications. So we simulate the system on known aerosol or water clouds. This is an example of simulated haze blobs synthesized from the viewpoint of one of the real cameras. And here are the corresponding reconstruction results as estimated by our tomography algorithm. Of course, we eventually made end-to-end experiments. Here's an example of reconstructed water clouds. Here we compare a real image to an image synthesized based on the reconstructed water clouds. Here is a cross-validation test. This image was not part of the viewpoints used by the reconstruction algorithm. The algorithm managed to roughly reconstruct it. But there is still a lot of room for improvement. In the real image, the gray part, encircled in yellow, is the base of a cloud. It is dark due to light extinction. Tomography misinterpreted it as the dark, clear sky, and this created a cloud void. Clearly, there is more research work to be done. This research is big science. During 7 years, we went from scratch, from a rough concept through development of theory, numerics, and all the way up to field experiments. All this via many challenges. We now hope you can see how common cameras can be turned into a large, sophisticated network to do radiometry and scattering tomography. And for the future, we believe this concept is scalable globally using cellular and Internet of Things infrastructure. It can complement satellites and active sensors. However, camera units should be made more like smartphones for reliability and scalability. Such a system is also a testbed for more research on scattering tomography algorithms. Thank you.
Really, really awesome work, Amit. So I just am amazed at how you guys have gone from from a hardware to the software end, and even the little washer on the camera is pretty cool. So I guess I'll start with the question that I have. So ignoring the projection in situ, which I know makes the problem more challenging from the ground from that point of view, but I was wondering if you could comment on if it's harder to solve this tomography problem of the clouds from above or below because of the location of where the sun is. So in the above case, when you're doing it from space, the sun reflects off and scatters towards the camera, but here it's the light that's more going through. So I'm wondering if that has an effect on the reconstruction quality.
I think each direction has its benefits. For example, if you are looking from above, you have to take into account the bed of the ground, for example. And so in previous work, we actually did it above the sea, so it would be more easy. When you look from the ground, actually clouds are, the light doesn't pass through the clouds, so so I'm not sure it's that benefit. It's easier because you're looking into a clear sky, which is a good background to work with. That I can tell.
I see. Okay. Yeah. I mean, I see clearly there are these pros and cons, but why it's challenging. I guess like that cloud extinction problem that that was highlighted towards the end maybe is because the cloud was too dense at that point.
I guess so it was a problem of possibly a local minima of the algorithm, specifically for the specific algorithm. The algorithm decided that it's easier for him to consider like dark sky than a dark cloud in that section.
Yeah, I mean, it tripped me up too. I would have guessed it was a sky. Okay, I have a question from Singbing. So he says, great work. How was the camera exposure selected? And is this setting the same across all cameras?
The setting is the same across all cameras, though even though they are calibrated separately, each one of them is calibrated separately. The lighting condition is calculated empirically, but it's modified according to the time of day because the light increases. So the exposure decreases as the sun is above, comes out, and so we compensate for the light. So we actually get a relatively even lighting along the day.
Okay.
But it's also a little point because we are taking each image is made of several, I think, 4 or 5 exposures of different exposures.
Oh, I see. Okay. So I have a question from Vishwanath. So he says, is it important to assume the sunlight is a parallel beam over the full area of the sensor network?
Yes. That's an assumption we do. At least at the scale of the network we are using.
Great. So I think that we've run out of time for questions, such a short amount of time. So I think we're going to move on. But if you guys have more questions, which I see them coming in as well, the authors will be online to help answer questions. So we're going to move on to the next paper now. So the next paper is by Shengxuan Chua and his collaborators on an approach to recover the material properties of scattering materials robustly through a blended kind of physics and learning-based approach. So he's going to present here, and then he'll also be here after for questions. So again, just put your questions in the comment section during the talk, and then I'll be able to ask them afterwards. All right, thanks.
Hello everyone, I am Cheng Qian, and I will discuss using learning-based techniques for inverse scattering. Scattering materials are everywhere. A cup of milk, an engagement ring, a forky highway, or our own skin are all made of scattering materials. Because of the ubiquity of these materials, applications related to scattering are critical in many different fields. For example, in medicine, recovering tissue scattering parameters is used to diagnose the presence of tumors. In AR/VR applications, knowing the scattering properties of translucent materials is necessary to reproduce them in virtual scenes. In industrial manufacturing, it is necessary to inspect the scattering behavior of fabricated objects in order to detect any defects. Importantly, in all of the above applications, there is increasing demand for computational techniques that can infer scattering properties in real time with minimum calibration and at the same time without sacrificing physical accuracy. All of these are instances of a problem we call inverse scattering. Given an image of a translucent object and potentially knowledge about the scene, we are looking to use computation to predict the optical properties of the underlying scattering material. We take first steps towards making inverse scattering possible in real time and in completely uncalibrated settings where no scene information is available. To this end, we first introduce a new inference pipeline, the inverse transport network, that combines neural networks with physics-based rendering to achieve both computational efficiency and physical accuracy at test time. We then show how to modify this pipeline so that it can tackle a class of ambiguities called similarity relations that confound inverse scattering. Finally, we create a new dataset of 30,000 rendered images of translucent materials and use it to evaluate our inverse scattering pipeline. Let's start with the first part. For this, it is worth taking a quick look at the physics of subsurface scattering. As a light source illuminates a translucent object, photons travel at its interior before being measured by a camera. This process can be modeled using radiative transfer, which describes materials using a set of optical parameters. Despite the complexity of subsurface scattering, we have powerful forward scattering algorithms that can simulate not only the physically accurate images of translucent objects, but also image derivatives with respect to scattering parameters. As we mentioned earlier, we are interested in the inverse process of mapping images to material properties. We can broadly categorize such inverse scattering techniques into two large groups. The first is analysis by synthesis techniques, which optimize for material parameters that, when combined with forward scattering simulation, produce images that match the inputs. Because we rely on forward scattering simulation, analysis by synthesis techniques are typically very accurate, but also very computationally expensive and require additional knowledge of the scene, geometry, and lighting. The second group of techniques approximates the inverse scattering function using a neural network. Such a network can be trained using a supervised loss comparing network outputs to ground truth parameters. These techniques are computationally efficient, requiring just a forward network pass at test time, and can operate without any additional scene knowledge. However, they are not physics aware, as they do not account for the forward scattering model. To combine the advantages of these two types of inverse scattering techniques, we propose a physics-aware learning pipeline that we call inverse transport network. It works by concatenating a neural network and a forward scattering simulator. During training, the network outputs material parameters which are used by the simulator to synthesize a new image. By requiring that this matches the input image, we force the neural network to act as the inverse of the forward scattering function. Our training loss has two terms. First, a supervised loss compares the network output to ground truth material parameters. Second, an unsupervised loss compares input and reconstructed images. In order to train the network, we need to backpropagate from the reconstructed image back to the network weights, which requires two sets of derivatives. First, the derivative of predicted parameters with respect to network weights, which is easily obtained using auto-differentiation. Second, the derivatives of the forward scattering process with respect to predictive parameters, which we compute by implementing our own volumetric Monte Carlo differentiable renderer. At test time, the inference requires only a forward pass through the network. Thus, inverse transport networks can predict material parameters efficiently without any geometry and lighting information, and in a physical-aware way thanks to the integration of forward scattering in training process. As we show in our experiments, inverse transport networks already significantly improve inverse scattering performance. Next, we discuss a couple of design choices that improve performance even further by enabling the networks to handle similarity relations in scattering. These similarity relations characterize ambiguities in the form of different material parameters that produce very similar appearance. We discuss two ways of overcoming these ambiguities. First, we take advantages of the fact that similarity relations are strongly dependent on lighting and geometry. Let's look at these two cubes made of materials satisfying similarity relations. They both look the same at thick and smooth surface parts, but they have different appearance near thin geometry features, such as edges. Therefore, we can mitigate similarity relations by training our network to emphasize appearance near geometric edges. To achieve this, we first use a simple algorithm to generate a per pixel weight map for any given input. Each pixel is weighted based on its distance from the nearest detected edge, as shown in these examples. Then, we use these per pixel weight maps to augment the appearance training loss so that it emphasizes the appearance difference near geometric edges. Our second approach for dealing with similarity relations is to reparameterize the material parameter space. We adopt a nonlinear transformation developed in the scattering literature so that materials with similarity appearance are closer in the transformed parameter space than in the standard parameter space of the radiative transfer. We now move on to some experiments evaluating our inverse scattering techniques. We evaluate 3 different networks. First, a baseline that is trained using only the supervised parameter loss. Second, our inverse transport network incorporating the unsupervised appearance loss. And third, our inverse transport network modified for similarity relations. All 3 networks use the same architecture inspired from the previous works. For our experiments, we created a new dataset of 30,000 HDR images using physically accurate monocolor rendering. We split our dataset into training and testing sets with no overlapping lighting and geometry conditions. We evaluate our networks in 2 settings. The first is an uncalibrated setting, where only a single image of the unknown object is available. We use each network to predict material parameters and evaluate the predictions using 3 metrics: a parameter loss comparing it to the ground truth parameters, an appearance loss comparing the reconstructed and input images, and an appearance loss between renderings for novel things. Here are some examples. We compare input images to images reconstructed from network predictions. From the error maps, we see that both of our networks reproduce the input appearance much more closely than the baseline, with the similarity networks producing the best matches. The network improves all our error metrics by 40 to 50% compared to baseline. We additionally evaluate our networks on photographs of 2 real objects. Each network uses only the photograph as input to predict material parameters, which we use to render approximate versions of the real thing for evaluation. The predicted parameters successfully approximate the appearance of the 2 objects, including important features such as intensity gradient near edges. We also evaluate our networks in a calibrated setting where, in addition to an input image, we have full knowledge of the same geometry and lighting. In this case, we can use analysis by synthesis together with gradient descent and our volumetric differentiable renderer to accurately infer the material parameters. We also use the prediction of our networks for initialization in order to significantly accelerate convergence and help avoid local minimum. We show an example for one image in our dataset. The initial predictions from both our 2 inverse transport networks produce images that match the ground truth appearance much more closely than the baseline. We then use these predictions to initialize gradient descent. We observe that at the same number of gradient descent iterations, analysis by synthesis initialized with our best network reproduce appearance better than when initialized with the baseline. Across our dataset, we have narrow improvement of 50% or a 2x convergence acceleration. To conclude, we have taken first steps towards enabling computationally efficient, uncalibrated inverse scattering through a learning architecture that incorporates forward scattering physics and accounts for similarity relations. Thank you for your attention, and please visit our website for all our data and code.
Thanks, Xingxing. Those were really impressive results. So it was really, really exciting to see how much better it was over the baseline, this new task. So I was wondering, like, as the questions start coming in, I have a question. So if you could give me just some intuition on why adding the decoder and measuring the air and image space helps so much. So I know that maybe you can just, restate some of the intuition for that, because I'm wondering, Is it because of the fact that different material properties might produce similar looking images? And if the networks performed more similarly on the parameter estimation rather than the image generation task?
Yeah, so one of the big reason is that the subsurface scattering process is a highly complex process due to the random walks of photon traveled inside the medium. Using a physically accurate forward scattering model inside a training process will help the neural network to learn this complex process. Also, as you mentioned, with the similarity relations, these ambiguities could cause a very strong problems in the inference process. So that by taking account for the similarity awareness and also the physical accurate model in the training, our network can outperform the baseline, like the pure learning method very well.
Okay, thank you. Yeah, impressive results. So I have a question here. It says, interesting work. Does the neural network use or assume some prior information about the object while training?
So during training, since we integrate a physically accurate forward scattering model inside of training, so the geometry and the lighting information are given for the forward scattering model.
Okay.
But at test time, no further information is needed. It's only a single image. It's input to the network for inference.
Okay, so in the neural network, there's no geometry or lighting information that's plugged in somehow?
For the neural network part, no, it's just a pure learning network, but okay, we only need the geometry and the light information for the appearance loss.
Oh, okay, I see. Yeah, that makes sense. Okay, we have a question from Berthy. How does this scale to objects with different material properties at different locations when you just don't have 3 parameters for the whole object? It varies per location.
Right now, we are the focus of this paper is on homogeneous material, homogeneous medium, where like these scattering parameters are constant across the entire object. But it is not possible to extend this work to handle heterogeneous materials. But you need to it requires computing the derivatives with much more parameters, basically, because it varies across this object.
Okay. So I have a question from Aditya. What happens if the anisotropy function is not Hennier-Greenstein function? Do you have to change the architecture of the deep net and retrain the network completely again?
Right now, the phase function we use is Hennier-Greenstein. But in order to yes, if you have a different phase function, I believe you have to model the entire data set with that phase function and retrain the network. But I think that with the Hennier-Greenstein phase function here, we are able to handle a large variety of materials.
Okay, makes sense. Okay. Thank you very much. I have to go on because we're past our time now, but there's lots of questions coming in. So if you and your other co-authors could help answer those questions during the session, that would be great. Great. So we're going to move on then to the final talk of the session. This next paper is by Yael Beckerman and her collaborators on an approach to better recover the true colors of underwater scenes by also recovering the water. And Yael will present, and Tali Trebitz will be here to answer questions after the talk. So again, put your questions in during the talk, and then we'll be able to answer them afterwards. Okay?
Hi, I'm Yael Beckerman from Tel Aviv University, and I will present our work, Unveiling Optical Properties in Underwater Images, a joint research with Shai Avidan from the Tel Aviv University and Tali Trebitz from the School of Marine Sciences at the University of Haifa. Underwater images suffer from low contrast, high color cast, blurriness, and noise. These effects are highly governed by the optical properties of the water, attenuation and scattering, In addition, the image deterioration increases with the object distance, as you can see in this example. In this work, we focus on robust estimation of the optical water properties for physics-based single image restoration. As you can see in our results, we are able to reconstruct even far objects that are almost invisible in the original image, and this is due to our superior parameter restoration. Physics-based single underwater image recovery is an ill-posed problem that is typically separated into two parts: estimating the water properties and using a prior to estimate transmission. Once these are estimated, the scene is recovered. While there is substantial work about suitable image priors for reconstruction, estimating water properties was relatively neglected so far. Nevertheless, these parameters have critical influence on the results. Here, we concentrate on robust estimation of these properties and show that this greatly improves results. A quick reminder about the underwater image formation model. The object radiance J is exponentially attenuated on the way to the camera. The attenuation depends on the attenuation coefficients beta, which are color dependent, and Z, which is the distance from the camera sensor to the object at pixel X. There is also an additive component that comes from scattering along the line of sight. This component increases with the object distance until it reaches a saturation value termed V. Note that since this is a physical model, the input image should be linear. If we examine the image formation model, we see that this equation is under constraint. Per pixel X, J and Z are unknowns. Vc and beta C represent the optical water properties and are global unknowns. That is, they are assumed to be uniform across the scene. These are the parameters we estimate in this work. What was done previously in single image methods? In the 50s, Jelov introduced a classification of water bodies based on their attenuation and categorized its observations into 10 water types, which represents all the water bodies in the world. Types 1 to 3 are oceanic waters that range from very clear to slightly mercury, and those suffixed with C represent coastal waters with increasing turbidity from 1 to 9. So far, these measurements were used to estimate the attenuation coefficients. These measurements are weather dependent, and to use them in RGB images, it is common to take their values at the peak camera sensitivity wavelength. Nevertheless, it was recently shown by Kanyak et al. That the manifestation of Jelov measurements in broadband images depends on many factors such as object distance, reflectance, etc. Therefore, the attenuation coefficients of RGB images are not physical parameters and cannot be taken directly from the J-Rolov measurements. Methods that are based on using specific values from the Jelov water types have an inherent limit of accuracy, as these numbers are usually not actual numbers that should be used. In contrast to this, our methods find the coefficients that explain the image scene in the best way without using preset values. Estimating the veiling light correctly is important for solving the underwater image formation equation for any dehazing method. The image formation model equation assumes a global veiling light for the entire image. However, very often this is not true. The sun is illuminating from an angle, etc. Therefore, methods that find the veiling light from the background pixels in the scene are prone to instabilities. Moreover, due to low visibility, the background detection is sometimes erroneous, inserting errors into the process. Like you see in this example, where part of the Rex bridge was detected as background. To overcome these issues, we propose to find a veiling light value that best fits the image formation model based on the given image and use information also from nearby objects. The full restoration pipeline consists of 4 main steps. First, we perform a global white balance ambient light correction on the linear input image. Then, we estimate the attenuation coefficients and the veiling light. Once they are estimated, any prior can, in theory, be used for restoration. We use the Haze line prior for recovery that also motivated our coefficient estimation. I will focus on steps 2 and 3, which are our main contributions. The Haze line prior was introduced in 2016 by Berman et al. It is based on the assumption that colors of objects all over the scene are clustered in RGB space. For example, here you can see 4 different color clusters and the respective pixels are scattered all over the image. What happens to these clusters under haze? Berman et al. Showed that they become lines in RGB space, spanned between the original color J and the veiling light color V. This can be seen when rearranging the equation as we did here. Note that this is correct under the assumption that the transmission does not depend on the color channel. Berman et al. Show how to find the haze lines and how to use them to restore the image. What happens underwater? As we saw there, the attenuation heavily depends on the wavelength, and therefore the lines become curves. Berman et al. Showed that if knowing the ratios between the attenuation coefficients in the color channels, which they took from the gel of water types, then the curves can be straightened and the haze line prior can be used to restore the image. We use this insight to estimate the attenuation coefficients ratios from the image data. When we look at this equation in log space, we can see it describes the line. The line's slope is the unknown beta ratio, and its intercept depends on the pixel's color. So when we scatterplot the data, we would expect to see many parallel lines. Here is an example scatterplot. Naturally, there are many pixel colors and the lines are adjacent. We look for the slope that fits most data. We do that by rotating the data in several angles, and for each angle we calculate a score based on the number of pixels in vertical bins. The angle with the highest score represents the slope we are looking for and results in an estimation of the attenuation coefficients ratios. We find the veiling light as follows. We use an initial estimate from background pixels. We perform a global contrast stretch on the image. We assume this yields ground truth in the nearby objects, as they are usually used to determine the stretch limits. We optimized for the final values using the initial estimate and the nearby ground truth pairs. And finally, some results. Here is a typical input image. And our result. Note the zoom-in area in the back. Where previously invisible rocks are now visible. Our method avoids artifacts, corrects the colors, and recovers far objects. And this is the recovered transmission map of this scene. That has a very good match with the ground truth. Comparing to recent methods, it can be seen that our results have better color and contrast, especially in the farther parts, as seen in the zoom-ins. The next image is more challenging since it was taken in around 20 meters deep and has low signal. Yet, our method succeeds to reconstruct the objects and the colors pretty well. As well as the transmission map of the scene. However, other methods tend to suffer from color skews and artifacts, and also amplifies the noise. These scenes were taken from the dataset recently released by Berman et al. That we used for evaluation. It contains 57 stereo images from 4 dive sites. The datasets enable quantitative evaluation through ground truth color and range information. Using this dataset, we performed extensive evaluation that is detailed in the paper. We compare our methods with 12 recent methods and, a spoiler alert, our method has the lowest color reconstruction errors. We also conduct an ablation study for all the method steps. Here's an example of the quantitative comparison. We tested 12 methods and compared performance across dive sites and on the entire dataset. The rest of the details are in the paper. Here are some results from a different dataset, and with this, I will be happy to take questions. Thank you.
Really nice paper, Tali, and it was a really clever idea to basically be finding those lines in the space. So I was actually wondering about the beta term and actually how. So you're saying that for a single body of water, it's not going to have one beta term. So I was wondering how does it change over time and over space? Is it pretty smooth in time and space, or and can you use that information?
Yeah, actually, we showed in previous CVPR's papers in my group that the beta terms are actually changed inside the scene because so the parameter that is uniform in the scene is the parameter that depends on the wavelength. But because there is wavelength dependent integration in the camera in each color channel, actually other parameters that are not physical optical properties of the water influence what we call the effective parameter that that the camera senses. So actually they change in the scene. They depend on the distance of the objects and the reflectance and so on. So what our method, the method we presented here, actually finds kind of an average parameter that it's not a physical parameter, but this is the parameter that enables the best scene reconstruction. But to your original question, it depends where you are. It can, I don't know, for example, we have a storm coming in tonight in Israel, so I'm sure the parameters will change overnight in the Mediterranean. So it really depends on the situation.
Interesting. Okay. So I have a question from Kaigo. Were the images D-gamma corrected before processing?
So these are linear images we use in linear images. It's a physics-based method. And that's why we use the dataset we previously published that has linear images. So the images we showed in the last slide are from a dataset that is not linear, and we didn't D-gamma correct them. The results are still good, but of course, when you have linear images as the input, they are better.
Okay. Another question. You said your algorithm estimates the veiling light from background pixels. How do you identify background pixels, or is this done manually?
No, it's done automatically. It's based on previous methods. So basically, we did it before, and also other papers kind of look for areas with a smooth, not a lot of edges or smooth areas that are in the top picture. What we show in this paper is that it's not a very stable method, and we show how to refine it.
Okay. And then I guess I have just a follow-on question to the one I asked earlier, because I'm interested in this fact that the beta is changing even in the scene. So were you able to do, or could you do synthetic experiments to see how much just capturing the mean beta, how that affects the result? I'm guessing obviously it'll be better than not getting that correctly, but I'm wondering how big of an improvement you can get if you actually know the per pixel beta.
Yeah, so we actually published this work in the last CVPR, and we showed that if you do range-dependent beta, it's easier. The reason is that in this work we used a single beta. Is just when you have range dependency, it's difficult to do a single image reconstruction because then. So for a single image reconstruction, we stayed with the same beta, although we know it's not the most accurate, but still we manage in this framework of the single image reconstruction, we managed to improve previous works by taking that into account.
Okay, yeah, makes sense. Okay, thank you. Thanks, Tali. I think we're out of time for questions now. But again, just as a reminder, there's going to be a session after this for authors to answer questions. So thank you again for attending the first session of ICCP. an exciting first set of papers. And the videos of the session will be available if you want to go back and rewatch the talks. And as I said, I know there's more questions that we weren't able to handle in our 3-minute Q&A time. So there'll be a session now where the authors will still be answering questions through the comment session of the comment thread of the video. And we're going to break now from the presentations. We have a keynote that will be in 1 hour, and then after that, we'll be back in 3 hours for the next set of paper presentations. Okay, thank you. Bye.